For the first time in weeks, astronomers can observe it again. Ground-based telescopes are now capturing clear images of 3I Atlas following its passage behind the solar disk. The post-perihelion recovery window has officially begun. Between November 13th and November 17th, 2025, the object passed through a zone where solar glare prevented any meaningful observation. Now, Southern Hemisphere facilities are reporting improved visibility conditions. Initial data shows changes in tail structure, brightness behavior, and possible jet activity that differ from pre-perihelion measurements. This recovery window represents the first opportunity to measure how close solar passage affected the object's physical properties. Observatories in Australia, Chile, and Argentina are now collecting photometric data, imaging tail morphology, and tracking brightness variations. The measurements will help refine models of interstellar object behavior during extreme solar heating. 3I Atlas disappeared from observable view on November 13, 2025. The object's trajectory brought it within angular proximity to the solar disk, creating conditions where telescope observation became impossible. CCD arrays cannot point within certain angular distances of the solar surface without risking sensor damage from scattered radiation. Safety protocols require minimum separation angles, typically 20 degrees for ground-based instruments and 30 to 40 degrees for space telescopes, depending on thermal protection specifications. For 4 days, no facility could track the object. It passed through perihelion, the closest point to the solar surface in its orbit, while remaining invisible to Earth-based observation networks. This period is standard for any object passing close to our star. The exclusion window exists not because of the object itself, but because of the overwhelming brightness differential between solar radiation and the comparatively faint light reflected from small celestial bodies. On November 17th, orbital geometry shifted. 3I Atlas moved far enough from the solar disk that Southern Hemisphere observatories could resume imaging. This marks the beginning of what astronomers call the post-perihelion recovery window. It represents the transition from solar interference to clear observational access. Southern Hemisphere facilities gain visibility first due to Earth's axial tilt and rotational position relative to the object's current coordinates. Northern Hemisphere telescopes will achieve optimal viewing geometry over the next 48 to 72 hours, as planetary rotation brings the object into their accessible sky regions. The improvement in data quality is substantial. Solar contamination has decreased dramatically. CCD blooming, the overflow of charge in detector pixels caused by excessive light input, has been reduced to manageable levels. Photometric measurements now have higher signal-to-noise ratios. Tail structure can be resolved with greater precision. Brightness gradients that were completely masked by scattered sunlight are now detectable. This represents standard improvement that occurs whenever an object moves beyond critical solar separation angles. Southern Hemisphere telescopes are now generating the first reliable post-perihelion datasets. The primary observations focus on 3 areas: tail structure, brightness behavior, and surface activity indicators. The tail morphology shows notable differences compared to pre-perihelion imaging. Before solar passage, observations documented tail fragmentation and structural inconsistency. Dust distribution appeared irregular. Certain sections showed reduced coherence. Now, post-perihelion imaging reveals increased structural stability. The tail has reformed into a more coherent configuration. Dust particles are aligning along a more defined axis. Brightness gradients indicate organized material distribution rather than fragmented dispersion. This behavior can be explained through delayed sublimation processes. Cometary nuclei often contain volatile materials buried beneath surface layers. During perihelion passage, extreme solar heating penetrates the surface, raising temperatures in subsurface regions. However, thermal conductivity limits how quickly heat propagates inward. This creates a thermal lag effect. Even as the object moves away from peak solar proximity, interior volatiles continue to reach sublimation temperatures. The delayed release of carbon dioxide, water, ice, or other compounds can produce renewed outgassing after perihelion, leading to tail reformation and structural stabilization. This phenomenon, while uncommon, has been documented in long-period comets with low thermal conductivity. 3I Atlas appears to be exhibiting similar behavior. The tail is not defying physics. It is demonstrating thermal lag dynamics consistent with subsurface volatile distribution and delayed outgassing response. Brightness measurements show stabilization compared to pre-perihelion variability. Before solar passage, 3I Atlas exhibited brightness fluctuations that did not align with standard sublimation curve predictions. These variations occurred at distances where most cometary bodies maintain relatively stable magnitude. The spikes suggested either non-uniform surface composition, rotational exposure of different albedo regions, or episodic outgassing from localized active areas. Current post-perihelion photometry shows reduced variability. Brightness levels are stabilizing into more predictable patterns. This suggests that whatever surface processes caused the pre-perihelion fluctuations have either concluded or entered a different activity phase. Continued monitoring over the next week will determine whether brightness continues to stabilize, begins a predictable decline as solar distance increases, or enters a new pattern of variation. The apparent reduction in erratic brightness behavior may indicate that perihelion heating altered surface properties. Volatile depletion in upper layers, thermal sintering of dust particles, or rotation rate changes induced by asymmetric outgassing could all contribute to modified photometric response. Each of these mechanisms has been observed in solar system comets under similar thermal stress conditions. Pre-perihelion observations identified 7 distinct brightness regions on the nucleus, interpreted as possible jet sources. The spacing and distribution of these features showed unusual symmetry. Typical cometary jets appear at locations determined by local surface composition, temperature variation, and topographic features. The resulting patterns are generally irregular. Symmetrical jet arrangements are rare because they require uniform distribution of volatile materials and thermal properties across the nucleus surface. With improved post-perihelion visibility, astronomers can now search for these features again. Early brightness contour mapping suggests that localized bright regions are still present. Certain areas of the nucleus show elevated luminosity compared to surrounding terrain, consistent with active outgassing zones. However, detailed jet structure mapping requires higher resolution imaging than is currently available. Spectroscopic confirmation remains impossible at present. 3I Atlas is still within angular proximity to solar glare that prevents spectroscopic instruments from operating safely. Spectrographs require extremely precise pointing and are highly sensitive to scattered light contamination. As angular separation increases over the next 7 to 10 days, spectroscopic observation will become feasible. This data will definitively identify the chemical composition of any active regions and confirm whether discrete jets exist or if the brightness variations represent more diffuse activity patterns. Several physical mechanisms could explain symmetrical bright regions without requiring unusual processes. Rotational dynamics combined with subsurface volatile distribution could create regularly spaced active zones. If the nucleus rotation axis aligns with compositional layering established during formation, solar heating could activate multiple sites at similar longitudes. Alternatively, impact cratering history might have created a symmetric pattern of subsurface fractures that channel volatiles to specific surface locations. Each of these explanations relies on well-understood physics. Symmetry, while uncommon, does not require mechanisms outside current cometary science frameworks. It simply suggests that 3I Atlas has a formation or collisional history that produced more uniform internal structure than is typical for small icy bodies. 3I Atlas travels in a retrograde orbit relative to the solar system's rotation direction. Its trajectory moves opposite to the motion of planets and most asteroids. Additionally, the orbital inclination is relatively low, meaning the path remains close to the ecliptic plane rather than approaching from high angles above or below the planetary orbital region. This combination is less common among interstellar objects, but not unprecedented. Orbital characteristics depend on the object's velocity vector when it entered the solar system's gravitational influence. That vector reflects the object's prior motion through the local interstellar medium, which is determined by the gravitational environment of its origin region and any perturbations encountered during travel between star systems. A retrograde, low-inclination orbit suggests the object approached from a specific direction relative to our solar system's motion through the galaxy. It does not indicate unusual physics. It indicates geometric circumstances of approach and capture into observable trajectory. Pre-perihelion tracking detected acceleration that could not be fully explained by gravitational forces alone. This non-gravitational acceleration is standard for cometary bodies. Outgassing produces thrust. When volatile materials sublimate and escape from the nucleus surface, they carry momentum. The reaction force accelerates the nucleus in the opposite direction. This jet thrust effect is well documented and routinely measured in comet orbital analysis. For 3I Atlas, the magnitude of non-gravitational acceleration did not precisely match the observed outgassing rate based on brightness measurements. This discrepancy has several possible explanations. The mass estimate may be incorrect, which would alter thrust calculations. The jet geometry may be more complex than surface brightness patterns suggest, with some outgassing occurring from regions not directly visible. Or the outgassing may be episodic, producing thrust during periods when observation was not occurring. NASA's Jet Propulsion Laboratory has recalculated the orbital trajectory using new position measurements obtained after perihelion. Perihelion passage always requires orbital solution updates because gravitational perturbations from the solar mass are strongest at closest approach. These perturbations modify the trajectory in ways that must be measured rather than predicted from earlier data. The updated orbital solution has not been published yet. When released, it will provide refined position predictions, improved uncertainty estimates, and better constraints on non-gravitational acceleration parameters. This will help determine whether the acceleration has changed during perihelion passage, remained constant, or fallen within expected ranges once post-perihelion mass and outgassing rates are properly accounted for. Space-based observatories have not released imagery of 3I Atlas yet. This is due to operational constraints rather than observation priorities. Hubble Space Telescope, James Webb Space Telescope, and other orbital platforms have strict sun avoidance angles built into their operational protocols. These restrictions protect sensitive instruments from thermal damage and prevent scattered light from saturating detectors. Each telescope has specific angular separation requirements. Hubble requires approximately 50 degrees separation between target and solar position. James Webb, with its more sensitive infrared detectors and thermal requirements, needs even greater separation, typically exceeding 85 degrees depending on instrument configuration. These are engineering requirements, not observational choices. As 3i Atlas continues moving away from the solar position in Earth's sky, it will eventually exceed these threshold angles. Ground-based telescopes will continue providing data throughout this period. Space-based observations will become available as angular separation increases. JWST, with the strictest pointing constraints, will likely be the last major facility to achieve observational access, potentially requiring another 2 to 3 weeks before the object moves into permissible pointing zones. This sequence is standard procedure for any object passing through perihelion. Ground-based facilities observe first, space telescopes follow as geometry permits. The data types differ, with space telescopes offering higher resolution and access to wavelengths blocked by Earth's atmosphere, but the observational sequence always follows the same geometric constraints. The next 72 hours represent a critical data collection period. Observatories worldwide are prioritizing 3 specific measurements. First, brightness stability. Continued photometric monitoring will establish whether the object's magnitude is stabilizing into a predictable decline pattern as it moves away from the solar heating zone, or whether variability continues. This determines whether the pre-perihelion brightness fluctuations were temporary effects of approaching peak thermal stress or represent ongoing activity driven by rotational or compositional factors. Second, tail morphology evolution. Daily imaging of the tail structure will reveal whether the current stable configuration persists, continues elongating as delayed outgassing proceeds, or begins fragmenting again as thermal input decreases. Tail behavior directly reflects dust production rate and the balance between volatile, sublimation, and recondensation as the nucleus cools. Third, surface activity mapping. High-resolution imaging will attempt to confirm the location and persistence of the bright regions identified in pre-perihelion data. If these features remain active and in similar positions, it constrains rotation rate and indicates long-lived compositional variations in the nucleus. If they have disappeared or moved, it suggests the features were temporary thermal response zones rather than permanent structural characteristics. Within 7 to 10 days, sufficient post-perihelion data will exist to construct direct comparisons with pre-perihelion baselines. Astronomers will be able to quantify changes in brightness, outgassing rate, tail density, and activity distribution. These measurements will refine thermal models, improve mass estimates, and better constrain the object's physical properties. The uncertainty lies not in whether data will arrive, but in what patterns it will reveal. 3i Atlas has already shown behavior that falls outside the most common range of cometary characteristics observed in solar system bodies. Whether this represents rare but explainable combinations of thermal and compositional properties, or indicates that interstellar objects have systematically different characteristics from solar system comets, will become clearer as the dataset grows. 3i Atlas is only the 3rd confirmed interstellar object detected passing through our solar system. The sample size remains extremely limited. 1i Oumuamua, discovered in 2017, showed unusual acceleration and elongated shape. 2i Borisov, discovered in 2019, appeared more similar to typical solar system comets in composition and behavior. 3i Atlas adds a third data point. Its characteristics differ from both predecessors. The tail regrowth pattern, brightness variability, possible jet symmetry, and orbital properties create a profile that does not match either previous interstellar visitor. This suggests that interstellar objects may have greater diversity than the small sample initially indicated. The observation raises questions about detection bias. All three confirmed interstellar objects were discovered because they passed relatively close to Earth and became bright enough for detection networks to identify them. Fainter objects, or those with trajectories that did not bring them near Earth's orbit, would pass through the solar system undetected. The current sample may represent only the most observable subset of a much larger population with more varied characteristics. Additionally, formation environments matter. Objects formed in different stellar systems experience different protoplanetary disk conditions, radiation environments, and collisional histories. An interstellar object carries information about its origin system's composition and dynamics. The diversity observed among the three confirmed objects may reflect the diversity of planet formation conditions across different stars in the Milky Way. These observations help refine the questions astronomers are now formulating. How common are interstellar objects passing through our solar system? What range of compositions and structures do they represent? How do formation conditions in other stellar systems differ from our own? Each detected object provides partial answers while revealing new areas requiring investigation. The post-perihelion recovery window is now open. Southern Hemisphere observatories are collecting data. Northern Hemisphere facilities will join within 2 days. Space telescopes will provide additional observations as geometric constraints allow. Over the next 2 weeks, the most complete data set ever obtained for an interstellar object during solar passage will become available. 3i Atlas continues moving outward. Every night, telescopes track its position, measure its brightness, and image its tail. The data accumulates, the models improve, and our understanding of objects traveling between stars becomes more detailed with each observation.